Okay, so welcome back, and now what we're going to do is we're going to start talking about some other tests for convergence when it comes to other series. Okay, so in the last several videos, in the last sections, we've been covering two large classes of series, the geometric series and the p-series. And so we know how to, or when, these series are convergent or divergent. And so we can use these two series to determine whether other series are convergent or divergent. And so that's going to lead us to what's called the comparison test. And so to start with, let's take a couple of series. And the two series are very similar to each other. We've got this series, which has the nth term 1 over n squared plus 1. And this is 1 over n squared. So they look very similar to each other. So how do we determine whether this here converges or diverges? So let's see how this goes. So first of all, notice that these two series are both have positive and they're both increasing partial sums. So they have positive partial sums, right? They have positive terms. And they're monotone increasing. Okay? So keep that in mind. The series are positive. The sequence of partial sums is monotone increasing. And furthermore, what else do we have? We know that for all, excuse me. We know that for all n, right, we know that this is true, so that 0 is less than 1 over n squared plus 1, which is less than 1 over n squared for all values of n. Okay? Or positive integers of n, I should say. Okay? So now if we look at the kth partial sum, let's look at the s of k, right? The kth partial sum of this one. So we know that if we look at s of k of this series here, we have this, okay, right? Which we know is less than the kth partial sum for this one. Oops. Right? And then, of course, this is going to be less than the infinite series. N equals 1 to infinity of 1 over n squared. Okay, so now, if we look at this chain of inequalities, what do we notice? Well, the series on the right converges. So we know this series converges, right? It's a convergent p-series. So we know that the sequence of partial sums for this one is bounded from above, right? And so we conclude that the series of partial sums, S of k, is a monotone increasing sequence that is bounded above. And so again, by the monotone convergence theorem, this also converges. Okay? So, what do we know? So we know that the sequence of partial sums for this partial sum converges, right? Why? It's positive increasing sequence. Okay? It's bounded from above, and therefore, by the monotone convergence theorem, this also converges. Which means that the infinite series also converges. Okay, now what if we consider another series? What if we consider this one? Okay, so let me consider one that's slightly different. Infinity. Okay, so now let's look at these two. So now I've got two other series. Now again, they look very similar, right? This nth term and this nth term looks very similar, very close together it seems like. And so they'll probably behave the same way. Now the sequence of partial sums of all of these is monotone increasing. Again, you've got positive, right? The terms are both all positive. All the terms are positive. And they're increasing. So these are monotone increasing. Okay? And so now we also know, again, notice that we have this relationship. So again, let's compare the terms. So this term here is 1 over n minus 1/2. So this is going to be bigger than this one. So in this case, we now have this is n minus 1/2 is greater than 1 over n. Okay? Which this is going to be, actually no, wrong side, like that. Okay? So now again, if we look at the partial sums, this means since this is always true, then that means for each of the partial sums, S of k, which is going to again be the partial sum from n equals 1 to k of 1 over n minus 1/2 is going to be greater than the summation for n equals 1 to, not infinity, k of 1 over n, which is going to be greater than what? The series from n equals 1 to infinity of 1 over n. Okay, so now let's compare these. Well, since the series, okay, so let's go back to this one, the one on the right. Okay, so if we look at that series, we know that this is a divergent series. This is the harmonic series. So we know this diverges. Now, this goes off to infinity. Well, this goes off to infinity, and this is smaller than this partial sum, then that would also force that the sequence of partial sums here must also go off to infinity and thus diverges. Okay? So in other words, since this is unbounded and diverges to infinity, then that means the sequence of partial sums of S sub k for this series here also is unbounded and hence diverges. And that's it. So now what we're going to do is we're going to dive into this a little bit further and show you how this works, why this works, and we'll do some more examples. Okay, and we'll get into the nitty-gritty and we'll get into the comparison theorem in detail, and we'll get to the theorem and things like that. Okay? Have a great day.